let's do this. One more lecture before the weekend. Woo. All right, so last time we got to this point, we now support file sharing. Our users can upload files using multi-part form submissions. We're going to parse that format, get everything, get those bytes of the file extracted, and store that file and send it to other users. A lot going on there, and we do get to the point where we support file sharing. And for our purposes, users are going to post images and videos for each other to enjoy. And we have something like this. So when we support this, we're going to have some path, some dynamic path that takes a file name. This path might be different for each of you. You might have different setups for it. If you're following the structure that's been set in the homeworks, you'll have it something like this, /public /image / the file name of that image. You'll have some path like this. If you want to use query strings or whatever else you want to do for it, if you want to do like just /image / file name, whatever you want to do, you're going to have something to this effect. You're going to be hosting file names, hosting files where the file name is a parameter of your path. And this is one of the reasons why we want the router to support regex. We can no longer say if the path is exactly this, then host that content. We could do that for homeworks 1 and 2. We could do that. It's a little bit of cut and pasting to say if path equals elephant, flamingo, etc., and host all of those images that way. But we can do that. Like, that's fine. But now that we're hosting images uploaded by users, we can no longer do that because we don't know what the file names are going to be. We can have some file naming convention that's image 1, image 2, image 3, but we don't even know how many files are going to be uploaded. And if we're hard coding our paths using if the path equals this, then we have to have an upper limit of how many images can be uploaded. So we can't reasonably do that anymore. We can't hard code our paths. We need some flexibility here. And the biggest flexibility is taking just the file name itself as part of the path and then hosting any file by name. Right, so you all have something like this. I assume quite a few of you already have something like this before homework 3, but this is what we'll have. And then somebody uploads this. They send this as their GET request, /public /image /tilde SSH RSA ID, and they just got your private encryption keys. So this is bad. We have to be very careful with this. When we have a path that can host files, we have to make sure that we're not opening ourselves up to attackers requesting any arbitrary file on our server. Because this is going to get your private encryption keys. The tilde is going to navigate to your home directory, and then navigating from your home directory to where your private RSA keys are. If you have any private RSA keys on a Linux system or Mac, this is where they're going to be, is in this directory. And the user's going to know that, or the attacker's going to know that, and they're going to request your private keys or anything. Once they can get one file, they can get every file on your server, and that's bad. So what we'll do, and this is where I had to shout out the answer to the lecture question because we didn't get to this part last time. But for our line of defenses for the homework, it suffices if you just remove any / characters from the file name. And this doesn't mean removing slashes from the path, like /image or /public /image. Those slashes can still be there. That's part of the pathing. But anything in the file name itself, once you have this file name parameter that you're expecting, the file name, if you remove any slashes, then that gets rid of this attack. If you're trying to launch this attack and you're not allowed to use any slashes, like just try to access a file without any slashes. The slashes are what let us navigate directory structures. If you can't move directories, then we're only hosting files that are in our images folder. So wherever our images are, that folder, that directory, they can get any file in there, but you should only be putting public files in there anyway. That's why we have a directory literally named public, because that's everything in there is public. It's open to the users. anybody can request any file in that directory. And then we can have these parameters that say, as long as you're starting with the public directory, you can get any file from there. So if we remove slashes, you can't move to a different directory, which means you have to be in the images directory. And an attacker can't get anything they're not supposed to get. If you want to have more defenses, so for the homework, you have to be protected against this attack. I recommend doing the slashes because that's the easiest thing to do. When you extract the file name, you extract this file name, and then you say file name equals filename.replace slash with empty string. Done. That's all you have to do. It's kind of like escaping your HTML. You just have to remember to do it. Make sure you're not open to this vulnerability. If you want to have some other line of defense, if you want to do something else other than remove slashes, that's fine as long as you're not open to the attack. And one of those things you can do is maintain a list of all of the valid files that can be requested. So check every time somebody uploads a file, add it to a list of files that people are allowed to request. And then when you get a request for a file, make sure it's on that list. If it's not on the list, don't serve it. And if it's on the list, give them that file. So that's like the strongest, most robust way to handle this. And this assumes that you have a naming convention for your files. Don't use the user-supplied file names and let somebody upload a file name ~/rsa.id or _id. Don't let them add that as their file name. You have to be controlling everything in those paths and then maintain that list of files that are allowed to be requested. But any way you can prevent this attack is fine, but we will test for this. It is a security thing, of course, so you have to be aware of that. To test for this is the way that I recommend to test. This is what we'll do during grading. If you launch this command in your command line, this is going to launch an attack that is going to attempt to request your server.py, assuming you're following the pathing structure that we have in the homework documents already, this /public/image/filename. If you're following that structure, then this attack is going to request your server.py code if your directory structure is the same as the handout stuff. So this is our first attack that we're going to launch during testing. If this serves up your server.py code, which should be private, your server code shouldn't be accessible to the users. That's server-side stuff. They shouldn't have any access to that. So we use this as a proof of concept. If we can get your server.py, that's what we try to get for testing this. If we can get your server.py, that means we can get any arbitrary file on your server, and you're vulnerable to this attack. So for your testing, the first thing you should do is launch this attack, and if it serves up server.py, you know it's going to be a 0 on that objective. If it doesn't, you're probably good. I'll say probably. The exceptions would be if you're trying to cheese this. I have to give these qualifiers because somebody's going to be like, well, this didn't serve up server.py, but somewhere in their server they have if path equals /public/image/server.py, then return a 404. Like somebody's going to do that, so I can't say it too strongly. But if you're not trying to cheese the assignment, you're doing everything legit, and this is your path for hosting images, and this doesn't serve up your server.py, then you should be good. So this is a way to test it. The reason we need this command is that the browser and curl, I haven't introduced what curl is, so I'll do that in a second here. The browser will simplify your paths. So this ... in a file system means going up one directory, but the browser treats paths as the same thing as a directory structure. So ... means go up a directory, and we just told it to go into the public directory, into the image directory, then go up a directory, then go up another directory. Well, that just brings us back to where we started. So the browser will simplify this to just /server.py. So the request that you actually get, if you type this in your browser, your URL bar, your address bar, that URL, what request actually goes through is /server.py is the path. So it doesn't do what you want it to do. Curl is a command line tool that lets you send HTTP requests via the command line. It has all kinds of power and flexibility that you can send custom commands. You can add extra headers. You can send post requests, put requests, whatever. You can do a lot with curl. It's kind of the Swiss Army knife, I guess, tool. You can do whatever you want. If you're wondering how to send a request, you can always go back down to all the way to curl. It's the most basic but most powerful thing. It's kind of like the C equivalent of HTTP tools, I guess, if you want to think of it that way. But it's very powerful. Curl will also simplify your request. So if you do this curl and then this URL, it'll simplify it to server.py. So we use the path as is flag. This path as is says, hey, I typed that URL because I wanted that URL exactly. Stop simplifying it for me. Stop doing work that I don't want you to do. And just take my damn path as the path for the request. And then it'll say, fine, I'll send this path. And then it'll launch the attack. So that's how I recommend doing your testing. And MIME type sniffing becomes even more important, much more important than it used to be. Now that we take file uploads from users, and we're saying, hey, send us your images and your videos, and they're going to send us their JavaScript and try to inject that JavaScript into everybody's browser. With MIME type sniffing disabled, we say it's an image, it must be an image, and the browser can't treat that as JavaScript. So MIME type sniffing, very, very important still, and much more so now. Let's see this in action. So I have my server. Looks like it's already running, but let's restart it because I think I made some changes. Oh. And on my server, I'm going to make that request public /image /... server.py. So I'm going to try to get my server.py code. And the request that I actually got, it simplified the path right down to /server.py. So you type that in your browser, you say, well, I'm not looking at my server.py code, so it must be good. No, it was the browser that simplified that. Same thing with curl. With curl, if I do curl HTTP localhost 8080 / public / image / ... I shouldn't have done this whole thing. Server.py, not found. And if I go back to my server, the request I actually got was /server.py. So curl also simplified my URL for me, even though I didn't want it to. So I'm not typing that whole thing again. I'm just going in my history. If I add the path as is, well, now I'm looking at my server code because I'm purposely vulnerable to this attack. And if I go to my server, I did get the full path. So that's how we can launch these attacks. I've heard students say it makes me nervous every time that they're going to go out there in the world. But they'll say, well, if you type that in the browser, it doesn't send that full path, so I'm already protected against it because the browser's going to protect me. Do not ever think like that. There's no such thing as front-end security. Please never, ever think there's ever such thing as front-end security. We're not going to rely on the browser to simplify that because, well, the attacker is just going to use curl. But they might go further than that. An attacker can send you any request at all. Like it's bytes coming over a TCP socket. A sophisticated attacker, what they're going to do, actually I haven't shown this off yet this semester, but what they're going to do is create a TCP client connection and send whatever the hell they want. They're going to literally type out whatever characters they want for that request. There's nothing stopping them from doing whatever they want. So they're going to launch this just with a TCP socket. They don't even have to use curl. So if you're saying, well, curl will simplify the pass too. No, somebody's just going to send raw bytes over a TCP connection. They don't have to use any HTTP anything. They don't have to use any of that stuff. They're just going to use TCP and send you whatever attack they want. The attacker has full control over this stuff. There is no front-end security. The attacker's going to do whatever the hell they want. They're not even going to use your front end in most cases. They're going to write their own code and their own scripts, and they can send anything they want to you. And since I have this up, I might as well run this one. I can do the same thing with TCP. Get my server.py. There's all my server.py code. Again, proof of concept that they could get any code or any file off of my file system with this path if I'm not protected against it. Remove those slashes, and you're good. I purposely leave this one open to this attack. Okay. I set all this up, and then I went out of the slides anyway. Thanks, Vlad. Yeah, so the server was running. I used curl to send a request to my server without using the browser. So curl was in place of my browser there. The server still has to be running, yes. Okay, let's talk about buffers. So the way TCP works, and before we can start talking about buffers, let's remember how TCP works. And I'll expand. Some of this I didn't even say when we talked about TCP the first time. But the way TCP works is you have this three-way handshake. You create a connection between client and server. And you're going to, once that connection is open, you can send any number of bytes back and forth, client to server, server to client. It's a stream of data. It's not one connection for send one message and then you're done. You can send a message, leave the connection open, later on decide that you want to send another message. TCP is going to make sure those messages arrive at their destination, but it's going to let you use one connection and send multiple messages, as much as data as you want over the stream, and it is two-way communication. Now, our use case is usually create a TCP connection, do the three-way handshake. Client sends me an HTTP request. I respond with an HTTP response, and then we kill the connection. Connection's done. If that client wants to send us another HTTP request, they're going to open another HTTP connection, another TCP connection, send us another HTTP request, we return with a response, and then kill the connection. That's our use case, but TCP is a lot more powerful than that. We can do a lot more than that. It is a continuous stream of bytes using two-way communication. I keep failing the extract credentials, but it passes all my tests, and the autograder just says error : I don't know if this is the way to ask that. I mean, if you show me after lecture, I could take a look at it. That's more of an office hours Piazza question. I can't really do anything during lecture with that one. It's weird it doesn't say anything for the error, though. Kind of do want to look at that one. Not right now, though. So it's a two-way communication, and we do sever the connection. If you see the connection keep alive header, you've probably seen that in your travels through this course at some point. That connection keep alive, that's the browser saying, hey, we can use this TCP connection for multiple HTTP requests. Like, I would like that to be able to have multiple requests over the same connection. That's what that keep alive header is saying. Now, we don't do that. Maybe someday I'll require that in 3.12. We don't do that. Whenever we get to the end of the handle method, what the handle method does is, the handle method is called whenever a TCP connection is established. So you get one handle method call per connection. Once that connection is made, handle is called by socket server. And then once we get to the end of the handle method, once that method resolves, so once your code gets to the end of that method call and the stack frame's gone, the socket server is going to disconnect that TCP connection. So we get to the end of the handle method. Socket server says, well, it looks like you're done with that connection. Let me go inform the client. And tells the browser, hey, they're done with this TCP connection. We're done. No more requests on this connection. And, goodness. And then if they need to send another HTTP request, they need to do the three-way handshake again, create another connection, send another HTTP request, and we send another response and sever the connection. We don't have to do that. You just don't let it get to the end of the handle method, and you can reuse that connection. But we don't do that in 3.12 because it'd just be one extra thing that we'd have to do. So that's how TCP works. And what's the issue? Why do we have to talk about buffering? Well, in most cases, we call this receive method. They delete half the letters here, but it's receive, not recv, not recv. Whenever I say the receive method, this is the one that I mean. So the receive method is going to receive bytes from the TCP stream that's been established. And this argument that we give it, we're giving it this 2048 if you didn't change the handout code. We get this 2048, and that's saying give me at most this many bytes from the TCP stream. Now, for most of our purposes, this was fine so far. Everything was less than 2048. I've noticed it. So the midterm reviews, which I forgot were even happening, came in, and I got comments, and there was a comment, there's so much talking, I can't even pay attention in this class. I never noticed that before. I'm looking around today. What the fuck, guys? Like, why are y'all talking during lecture? Over here, here, back there. Y'all are talking like through the whole lecture. Do you know how ignorant that is? How frustrating that is for the people around you to have to listen to you talking about just, whatever throughout the whole lecture. I don't even know what you're talking about. But just cut it out. Like, what the hell? This is college. If you want to talk to each other, just don't come here. Like, you don't even have to be here. You're here presumably just for the lecture question. But, like, I don't know. And I don't know, if I want to talk to someone during lecture, if I were in that position, I think about, like, what would I do? Like, we have the internet now. Just go in a group chat. Type it up. Like, you can talk all you want. You just type. It's easy. But I'm starting to watch it more. And if I don't catch it, somebody is being distracting, snitch on them. Let me know. This ain't a snitches get stitches scenario. It's not like a terrible thing. Like, if you're talking in class, you're only affecting everyone around you. You're hurting everybody around you. It's not other situations where it's like, let them have their fun. It's not one of those things. Send it in chat. Say, 2 rows from the back, this person's talking. I'll do something. I don't know. I usually just stare at you. If I'm staring at you and not talking, it means you're doing that. But anyway, I don't want to dwell. I hate having to do things like that, but I really don't notice it. I noticed it, when they said that feedback, because I don't notice it. It's hard to notice up here. If I hear you, that means you're being completely, like, way too ridiculously loud. It's hard to hear the things from down here. I have to watch for your lips to move. I have to actually spot it, and it's hard to spot. Okay. Anyway, let's talk about buffering. Back on track. This is the maximum number of bytes, and usually that's fine. 2048 gets us through homeworks 1 and homework 2, and isn't going to get us through homework 3. Once we have file uploads, this buffer size is not going to do it because we're going to have something like this, where content length is way more than 2048, and sometimes it's going to be way, way more than 2048. We're going to test with files that are several megabytes in size. So this number is going to be bigger than this number, and we're going to have to, what we're going to end up doing is having to read from the TCP socket multiple times to be able to get all of the requests. So the request can't be read in one go anymore. We have to go to the socket multiple times. So we have to call receive multiple times. This is going to be our reality moving forward. How do we do this? We could just up this value, and this is what some of you will try. It doesn't work. One, we're going to look for this. It's in the testing procedures to look for this, but we don't even have to look for it because it won't work. And I'll give a demo of why that doesn't work, but it just doesn't work. Internal, I'll say it right now anyway. Internal, the socket server will cap this. Even if you give it 1 billion for an argument, it will cap that at like 64. I've seen it go up to, I think 128 was the max, 128K. but it will cap that, and we're going to make sure that we go over that cap. So what happens when we have multiple receives that need to be called to be able to get the thing? Well, call it multiple times. I kind of spoiled that one, but call it multiple times. So with buffers, or without buffers, with our get requests were fine. We would just receive the whole thing. We would call receive, we'd get the entire request in one go, and that was fine for us. But what happens when we have a lot of data? Our case is image uploads and video uploads, but this could also be streaming video where somebody's going live for hours. We're not going to wait for them to end before we start processing this request. We have to process it on the go, and we're going to have to call receive multiple times. What if it's a large piece of data? What if the sender sent half of the request, and then their internet went out momentarily, and then sent the rest of the request? What happens then? Now we have to call receive multiple times to be able to get those bytes. And we'll go into what the receive method does. I want to make sure I break that down, what it exactly it is doing for all those situations. But we can't get all those bytes in a single call. We have to make sure that we get the entire request before we start processing that request, before we try to get the bytes of a file, extract those bytes, save it to disk, do all that stuff we talked about last time. We have to make sure we have the entire file first. So how are we going to do this? We know we're going to have to call receive multiple times, but how many times? How are we going to know when to stop? So we need some way to do that. We're going to call receive, store the bytes that we get in some data structure. It's already in a data structure, so an array of bytes, and keep calling receive and appending to that data structure. Python does this with just the plus operator. You take two byte arrays, plus them together, that smashes them together, does just like string concatenation, does what you want. So how are we going to do that? Here's our exact procedure in one slide. When we're receiving a large HTTP request, which this code will end up being applied for every HTTP request, but it'll not be needed for a lot of them. We're going to read from the socket. We're going to go to our socket and call receive one time, just like we do now. When we call receive, we're going to assume, this is one safe assumption that you can make in this course, is that you'll get all of the headers in the first call to receive. All of the headers and the first blank line, that first /r/n/r/n. You'll get all of that. That means you can parse the headers. Call receive once, then parse the headers, and you're looking for that content length header. We're on the other side of content length now. When we said content length off by a byte, either the server's going to hang or you're going to be missing some of your bytes. We're on the other side of that now. We're going to parse the headers, extract the content length header, store this value, and buffer until we read content length number of bytes after the blank line sequence. So after this first instance of /r/n/r/n, there will be content length number of bytes, and we can't fully process this request until we read that many bytes of the body of the request. Just like when we're sending the responses, content length is only the number of bytes of the body, not including the headers. It's the bytes in the body. Same thing when we're receiving bytes. Its content length is after this sequence. So make sure we're reading the exact right number of bytes from content length. So we're buffering. This is our buffering stage. We're going to have some code in here that says something to the effect of, well, number of bytes from the body read is less than content length. Then keep calling receive and appending to your data structure that stores all the received bytes from your request. That's the procedure. So any questions on that? This slide, in one slide, pretty much shows what you're going to have to do with buffering in your code. And the rest of the slides you have to understand to see why and how we're buffering. But this is the crux of it right here. Okay, let's talk about a few more details then. Here's some assumptions you can make in your homework. I already said this one, but you can assume that the first call to receive is going to have all of the headers and the first blank line. It might also contain some bytes of the body, but it will at least contain the headers and the blank line, the first blank line character, or the first blank line sequence. That's a very convenient assumption to have, very important assumption to have, because then you call receive one time. You can parse the headers to get your content length, and then decide whether or not you need to enter your buffering state to see if that's something that's needed. Or if it's a GET request and the content length header doesn't even exist, you don't have to buffer at all because you have the entire request. If you have the headers and that blank line, that's the entire request if it's a GET request. So you're done. You don't have to do any buffering, and you can start processing that request. This will be different in Chrome and Firefox, and I'll demo both of them. Chrome and Chromium browsers, most of the time, it did something different during my demo in the other lecture, but most of the time, it will only send the headers in the first request. What Chromium will do is take the headers and that blank line character, it'll prepare those, send those over the TCP socket during file uploads specifically, for large file uploads. It'll send the headers, and then it'll go read the file, process the file, and then send the header. And there's enough of a delay in there that when you call receive the first time, you will only get the headers the first time, and then you call receive again, and you'll start getting the bytes of the file. Firefox won't do that. Firefox will prepare the entire request and then ship it, so you get the first 2048 bytes from the first call, which will include some bytes of the image itself. So two different things. It's important to be able to handle both of those cases. And the next assumption, we're going to test with large files. This, again, won't work anyway, but just don't do it at all. This won't work, but we're also looking for it. Don't change the buffer size. If you keep it at 2048, your code should work fine with 2048. Hell, your code should work fine if you change it to 1. But the code does go way slow if you change it to 1. But 2048 is a fine number. Leave it at that. Your code should be able to handle that. And remember, just so make sure I say this enough times so I hopefully don't ever see this in office hours, is the content length does not include any of the bytes of the header or the blank line character. The content length is only the bytes of the body. So in your buffering loop, if you're counting all of the bytes of the entire request, you're going to be missing the last chunk of that file, the last up to 2048 bytes of the file. You're going to be missing because your buffering was off. And in fact, you'll be missing it sometimes. Sometimes you actually get the whole thing. Just depends on how all the numbers line up. So make sure you're checking your content length against just the bytes of the body of the request. Okay, any questions on all this? At this point, LO1, LO2 on homework 3, that's all fair game. You have everything you need for those. Now that we have buffering, that was the last part for LO2. And LO3 will have everything on Monday. You have most of it right now. The only real thing that I have to talk about, LO3 is video uploads. The only thing I really have to talk about for LO3 is how to display videos on the front end. It's only front end stuff. You have everything on the back end to support MP4s. They're, based on what we talked about so far, you're actually just taking the file uploads as bytes. Doesn't matter if those bytes are a JPEG, a GIF, an MP4. It doesn't matter. It could be text. It could be anything, and your server handles it. You handle arbitrary file uploads at this point. We just happen to be doing images. But there's nothing special when it switches to movies. It's just how to display the movie to the user. So we're mostly through LO3, just a little front-end stuff I have to talk about on Monday. And then the AOs will be next week. AO1 I might not even talk about at all. I'll have to mention it, but it's more of a research task. And then LO2 I had to talk quite a bit about in lecture. Or sorry, AO1 and AO2 I meant. So any questions on anything? Up until LO2 of homework 3, that's where we're at. Okay, let's do demos. Oh, I ran testing client. Let's go back to server. Server's still running. And I have my code. It's the standard code that you should have. We're reading, we're printing the received data, which was in the handout code. It was a little different. I changed it just a little bit here. Calling the request constructor and then having the router handle that request. this. Oh, I want to talk about all of the stuff that receive does. So receive does quite a few different things. Before I do the demo, I got to talk about this. So receive, there's like 4 different situations for the receive method. The one we talked about, it's going to read up to 2048 bytes from the TCP stream. Now, it's up to 2048 bytes of the bytes that are ready to be read. So there's a few situations here. One, there might not be any bytes to be read. If there's no bytes ready to be read from the TCP stream, this method hangs. It just sits there. That's why this method always is returning, almost always, is returning something, because it'll sit there and wait for the client to send something, and you don't have to have any code on your end that says, wait for the client to actually send us something and then receive it. You call receive, and receive just sits there and waits for bytes to be sent. And if the client never sends anything, your server hangs forever. So if there are no bytes to be sent, it hangs. Once there are bytes ready, as soon as there are bytes ready, it will return up to 2048 bytes of them. So if there's less than 2048 bytes that are ready to read, it'll give you those bytes and no more. This is why in Chrome, when it sends just the headers, it'll return less than 2048 bytes to you, because those are the bytes that are ready. But that doesn't mean you got the full request. Some students will like to do, if I've received less than 2040, or if I've received exactly 2048 bytes, then we're buffering, baby. That doesn't quite work, because that first read on Chromium browsers is going to be less than 2048, even with a large file upload. So it's going to send whatever's ready. If there's just a little bit ready, it'll send it to you. If there's 1 byte ready, it's going to send it to you, even if there are a billion more bytes coming. And then if there are more bytes ready, if there's a megabyte of data ready, sitting there waiting to be read, it's going to return the first 2048 bytes of that data. That's the one we kind of talked about at length in the slides. And the final scenario is if the client severed the connection for any reason, and we call receive on a TCP connection that's been disconnected, it'll return an empty byte array. So if you ever see an empty byte array, that means the client severed the connection. And it can help to have this. You don't need this unless you have a bug, but it can help to have it in case you do have bugs. The bug doesn't blow up your whole server. I'm going to add, if I've received nothing, bless you, if I've received nothing, then just return, get out of this method, close. The connection's already closed, so let's end this handle method and get rid of, do a little bookkeeping, get rid of this connection. I have it here because what I'm going to do is going to really break things. So I have it here for the demo today. But it can't hurt to have that just in case something goes wrong, having that check and then handling that. Because if you have an empty received data and you try to throw that into your request constructor and try to parse the first line and get the HTTP method and the path and everything, it's going to blow up. You're going to get all kinds of index out of bounds errors, and your server is going to blow up. Okay. So that's all the modes of receive. That's what receive is doing. It's a very powerful method. It does a lot for you. So with all that, server's running. Let's go to the browser. We did server.py. I want the home page again. And I'm going to upload a file. Oops. Carefully click the right thing. And I'm going to send this elephant small, just the smallest image we have, so we can start testing this thing. When I send that, I'm going to see, first of all the requests. And I say this a lot. I feel like I've had to say this a lot in office hours, so maybe I haven't been super clear in lecture. To get test cases, run your server, play around on the front end with whatever the user is going to do. And with the handout code, you should have this chunk of code printing to the screen. It gives you very clearly, very cleanly, exactly what the browser is sending when you send a request. So one thing that I've been saying a lot in office hours is do this. Jesse, password, post. Chat history, WebSocket, public, homepage, and register. I have a request, a register request. in the exact format that your extract credentials is expecting. Now, most of you should be beyond this point by now, but beyond this exact objective. But the point remains that this is how you can generate your test cases. This is exactly the correct format that the browser is going to create, and then grab your test cases like this. This is how I got the test cases for the actual grader. Is I'm letting the browser generate it for me, so I'm not risking having some typos where I messed up the format because I was manually typing my test cases. Let the browser generate that for you. Now I have it in the exact format that I'm expecting, and I can write my test case, call extract credentials, and make sure I get Jesse and password out of this exact input. Then, if I'm passing that test case, I'm feeling really good. I'll create another one for login. If I'm passing both of those, it's almost certain that my code is going to be good at that point. But let's take a look at that image we uploaded. We got a little sidetrack there. We have post media uploads. That's the path that I gave my form. And we can see the request. We got 1560 bytes. And we can look. We have the bytes of the image, clearly not text, so we can't convert this to text because we'll get in trouble with that. And we do actually see the end boundary. We do have that optional new line character at the end after our last boundary that we talked about in the slides. But we do see the end of it, so we got the entire request in one go because we uploaded a very small image. So let's do this again with a bigger image. Dumb. I'm going to do that again. I don't know why it's inconsistent. I'm going to go for a massive image. I'm going to go with Chrome. Oh, shit. Not going to go with Chrome. I'm just going to send another one. I'm going to send it again. Let's try elephant. This is what I mean. It's inconsistent. You got to... Yeah, here it is. So now it did it. So post media uploads, I only got the headers. I'm calling receive one time. I only got the headers. All the other times, with similar sized images even, I got some bytes of the image itself when I sent that request. But here, I got just the headers. And if I do this in Firefox, let me just refresh. Looks like I was already doing it in the other lecture. Media upload, this is from Firefox. Notice that the boundary is in a very different format. That boundary we've been seeing, that's only Chromium browsers. That's what they choose. Firefox does something completely different. And this is really hard to see that there's 2 extra dashes here than here. You can't eyeball that anymore. And Firefox will always send, anytime I've seen it, maybe it does vary. Anytime I've used Firefox for uploads, it will send part of the image every single time. So if you're testing and your specific version of your Chromium-based browser always only sends the headers, this is the reason why I say this, because I see this every semester, only sends the headers and everything works fine for you, you submit TAs, they test in Firefox and Chrome, they test in Firefox, and you're getting some bytes of the image in your request, and in your parsing code, when you're parsing the headers, you're saying receive one time, and then convert that whole thing to a string and parse the headers. Well, when we test in Firefox and there's bytes of the image in there, your converting to a string there is going to blow up. You get a 1 on that objective, and you say, it worked on my laptop, and then we say, doesn't work in Firefox, you never tested in Firefox clearly, and you didn't pay attention when I said this in lecture. That's an easy 1 on the objective. You're never getting those points back. So be careful with that one. Oh, I think I did elephant small. This is actually the entire request. But even for large images, Firefox will send the whole thing. Okay, so let's get a little more creative with this, and I have to be a little careful how I do this to make sure I can do it. That should be fine. I'm going to change my server to call receive multiple times. So I only call receive once here. I'm not buffering, so I didn't even get the rest of the request. So let's make sure we get the rest of the request, and to absolutely make sure I do, I'm going to write an infinite loop. Well does not start with a capital. I'm going to write an infinite loop here and just keep receiving from the buffer. So I'm going to call receive, print out what I get, call receive again, and just keep looping forever and never actually process the request. I had to be careful on the front end because I can't get the home page again once I restart this server. because I killed that functionality. Connection refused. I don't want testing client. I want server. And then I'll upload elephant again. Let me click it just to make sure it's sending. And now, actually I shouldn't have done elephant. It's a bad one. But now every time I call receive, I'm getting more bytes of the image. I'm getting more and more bytes, and I'm gonna redo this to not print out what I'm actually receiving. Now I just want to print out the number of bytes that I'm receiving each time. So let's stop this again. But we are getting bytes of the image. I wanted to do that, but I usually, never mind. Refresh. And now we can see all our buffering, see how many times we had to call receive to be able to get this image. We did happen to get parts of the image on the first request. I'm telling you, it's inconsistent. It makes it for some really fun bugs to debug. It's really frustrating. The solution to that, by the way, is to look for the first /r/n/r/n. Everything before that you can convert to a string, but don't just call receive and convert it to a string, because it's going to get you a 1 on the objective easy. But we have to call quite a few times here. And if I upload a larger image, lots and lots of times, lots of calls to be able to get that full request. So what some of you will be tempted to do is to just add a whole bunch of zeros onto the end of this. That should be enough. Restart the server. Resend the image. I knew that when I was doing it. I had too many zeros and overflowed an int. Oh, come on. Not right at the end. Don't crash on me now. There we go. So even when I put a ridiculously large number there is an internal limit to the number of bytes that we're going to get each time. Like sometimes we get 52 bytes. That's fun. I think this is how fast that the network can send. Well, not even the network. It's internal to my laptop here. But how fast the bytes can even be sent. And we're getting at most 32K per read, per call of receive. So even jacking this up to a really high number, it doesn't even work when we have really large images. So we can't do that. We have to buffer. We're going to